Okay, for what we have in number 1, it says to graph the function g of x is equal to 4 raised to the x minus 1, and to give its domain and range using interval notation. Okay, so again, g of x, this is a functional notation for what we otherwise say is going to be y. And so we have, just for the setup, say y is equal to g to the x, or g of x is equal to 4 to the x minus 1. Okay, now let me mention, okay, now for the domain, now we can have x to be any real value and y come out to be an amount that is defined in the real number system. So if I plug in any negative, 0, or positive value for x, for 4 to the x, and then take away 1, y is going to be a defined value. So I can plug in anything for x, whereupon the domain is going to be the set of all real numbers. Okay, so we have between negative and positive infinity. Now, for what we have in the case of the range will be in reference to the set of y values. Now, let me mention, okay, if I have 4 to the negative power, or 4 to the 0, or 4 to a positive, the results will always come out to a positive. And the smallest amount that 4 to the x can be, like they have like 4 to almost like negative infinity, that's just going to be like the reciprocal of 4 raised to a positive power. So the smallest that 4 to the x can be will be the smallest positive value that exists. Okay, so it's going to be greater than 0. And if I have like 0 minus 1, your smallest value for y is going to be the smallest value that is greater than negative 1. So we have for the range, you have those values of y that will be greater than negative 1. Okay, so just to kind of give you an idea, say you have like 4 to, let's say, the negative infinity minus 1, and you have like 0.000 minus 1, and so the smallest positive value that exists, okay, for what we have here will stem from 4 to the negative infinity, and take away 1, so the smallest positive, or I should say the smallest possible value for y is going to be the, in this case, that which we have to be greater than negative 1. And just lining up what we have here. So we have for the domain, again, the set of x values, you have the set of all real numbers. And for the range, okay, you have the smallest possible value that is greater than negative 1, and we have going all the way out to infinity. And let me mention, okay, so just some points that we have here, like if I have looking for x and y values, if I have like x is at 1, okay, we have for y, we have 4 to the first minus 1. 4 to the first is going to be 4 minus 1, so we have is equal to 3. So we have as an ordered pair in the x, y coordinate system, we're going to have at 1, 3. And say if I have x at 0, okay, now we have 4 to the 0. That's going to be at 1. Take away 1. 4 to the 0 is 1 minus 1. And that is equal to 0. So we're going to have the origin, whereupon we have 0, 0. And I'll just take one more point here. And we have 4 to the negative 1 minus 1. 4 to the negative 1, that is going to be 1/4 minus 1. So that'll be minus 3/4. So another point that we would have would be negative 1 and negative 3/4. Okay, so in looking at what we have now, referencing back to what we have in the case of the graphing. Okay, so again, we had for the domain, in the case of the domain, okay, so we have the set of all real numbers, so going from negative to positive infinity. And for what we have in the case of the range, okay, we have tangent to but above negative 1. We have going out to infinity. And in looking at what we have in terms of graphing horizontal asymptote, again, y cannot be equal to negative 1. All the values will be greater than negative 1. And in terms of plotting points, and again, we had 1 point to be at 1, 3. And we had also the origin whereupon we had at 0, 0. And then so we have our graph. Okay, it only shows up so well. So we had the origin and 1, 3, and checking what we have for the results, and we have the answer to be correct. Okay, for what we have in problem number 2, it says here, if the rate of inflation is 2.8% per year, the future price, P of t in dollars, of a certain item can be modeled by the following exponential function, where t is the number of years from today. So we have P of t is equal to 3,000 times the quantity of 1.028 raised to the t power. And it says to find the current price of the item and the price 9 years from today. And it says to round your answers to the nearest dollar as necessary. Okay, so we have with the current price, okay, this will be the price as of today. And so in looking at what we have in modeling, okay, so we have with our formula, okay, so you have P of t, and we have is equal to 3,000 times 1.028 raised to the t power. So the current price we have whenever t is equal to 0, so you have 3,000 times 1.028 to the 0, and a non-zero number raised to the 0 power is going to be equal to 1. And so we have for the current price, okay, that is going to be at $3,000. Now for the price 9 years from today, for the future value, we're looking at 3,000 times 1.028 raised to the t power, whereupon t is equal to 9. And so just taking the numbers that we have here. Now we have with, in the case of 1.028 taken to the 9th power, and we have just in the case of numbers I have here, so I have 3,000, and I have times 1.28214, and if I take to the nearest penny, okay, so this would be about $3,846.44. Okay, so in looking at what we have, referencing back to what we have in the problem, so we have for the current price, okay, we have $3,000, and for the future value, okay, we have 9 years from today, you have 3,846.44. It's just rounding to the nearest dollar. Okay, so you have $3,846. And the result is correct. Okay, for what we have in number 3, we have a species of animal is discovered on an island. Suppose that the population size P of t of the species can be modeled by the following function, where time t is measured in years. Okay, so we have this particular formula, and it says to find the initial population size of the species, as well as the population size after 8 years, and it says to round your answers to the nearest whole number as necessary. Okay, so we have in working with the formula that we have regarding population, so for the initial population, okay, so you have starting out at t is equal to 0, and so we're going to have, in this case, right, so you have P of t with t at 0. So we have the initial population, we have at P of 0, and we have is equal to 520 all over 1 plus 2 times e to the 0, negative 0.4 times 0 is 0, and again, non-zero number to the 0 power is equal to 1. And so we have, in this case, all right, so you have 520 over 1 plus 2. So we have 520 over 3. And so, and just taking to what we have to the nearest whole number, okay, so this will come out to actually a tad over 173, but it would round down to 173 if we are rounding to the nearest whole number. Now, after 8 years, okay, where we have t is equal to 8, so we have p of t becomes p of 8, and taking what we have with the numbers, okay, so we have 520 all over 1 plus 2 times e to negative 0.4 times 8. So we're going to have 520 all over what is going to be 1 plus 2 times e. And negative 0.4 times 8, this will be negative 3.2. So we have 520 all over 1 plus 2 times. Okay, now for what we have in the case of taking what we have for e to the negative 3.2, okay, so we have 0.0407, and if I multiply by 2 and add 1, okay, so we're looking at about 1.0815, and just holding on to that decimal. And it's going to turn out that, okay, to about the nearest whole number, okay, we have about 481. So you have 480.8028, which will round up to 481. Okay, so just taking what we have with the numbers. So the initial population you have at 173, and we have for the population size after 8 years, okay, so you have about 481, and checking the results. And the number is correct. Okay, for what we have in problem number 4, suppose Sam places $2,000 in an account that pays 7% interest compounded each year. Assume that no withdrawals are made from the account. Follow the instructions below, do not do any rounding, and it says to find, first of all, the amount in the account at the end of 1 year. Okay, so we have annual compounding of interest, and we have just taking what we have in the formula. We have a is equal to p times the quantity of 1 plus r raised to the t degree, and again p represents the amount that is put in, which we will have at $2,000, and we have for r that is rate of interest, so we have at 7%, and in the formula we're going to record the decimal equivalent without the percent, so 7% would translate to 0.07. And so for the amount after 1 year, and using this formula, so you have 2,000 times the quantity of 1 plus 0.07, and we have to the t's, and t is only 1, so we have 2,000 times 1.07, and for what is going to occur in this case is that the future value after 1 year, that is going to be at $2,140. Now, for what the future value is going to be after 2 years, okay, so you have the same formula. So you have 2,000. Again, we have 1 plus r, we have 1 plus 0.07, and to the t we have to the second, and here we have 2,000 times 1.07 to the second, and for 1.07, okay, raised to the second, so 1.1449, and multiply by 2,000, so we have at 2289.80. Okay, and to the nearest dollar, okay, that would be about $2,290. Okay, so we have just checking what we have for the outputs. Okay, so we have 2140, and after 2 years, okay, it says do not do any rounding. Okay, so we have 2289.80, and checking the results in this case, and the answer is correct. Okay, for number 5, a principal of $2,700 is invested at 4.75% interest compounded annually, and the question posed is how much would the investment be worth after 9 years? And for what we have in this case, all right, so we still had the same formula that was used in number 4, so we're still looking at annual compounding. Okay, so you have A is equal to P times the quantity of 1 plus R raised to the T degree. Now we have with the principal what is put in. Okay, we have at $2,700, and for the rate we have 4.75%, and converting to a non-percent decimal value we have at 0.0475, and we're looking at the future value after 9 years. So putting in the quantities, okay, so we have 2,700 times what's going to be 1 plus 0.0475, and to the T power we have to the 9th power. So you have 2,700 times 1.0475 to the 9th power. So we have with this exponential base, so you have 1.0475 taken to the 9th power. So you have a little bit over 1.5, so you have 1.5184, and just keeping the decimals, and then multiplying by 2,700. So you have about $4,099.68. Okay, and so we have, so you have here, okay, so rounding to the nearest dollar. So this will be about $4,100. And just testing what we have in the result. As I enter, and we have upon awaiting the result. And the answer is correct. Okay, for what we have in number 6, an initial amount of $3,500 is invested in an account at an interest rate of 8% per year, compounded continuously. Assuming that no withdrawals are made, find the amount in the account after 4 years. And it says do not round any intermediate computations, and round your answer to the nearest cent. Okay, so we have with continuous compounding, we have A is equal to P times E raised to the R times T degree. So we have what is put in, we have 3,500, and the rate of interest we have 8%, and as a non-percent decimal again this will translate out to 0.08, and the time span is going to be 4 years. So in looking at the future value, so you have P, again we have it 3,500, and we have times E, and this will be raised to the R times T degree. So R we have at 0.08, and T we have at 4. So we are looking at 3,500 times E raised to the 0.32 degree. And again, we have with E to the 0.32 degree. And so we have here with E to the, so E to the 0.32 degree, we have right at 1.377, and keeping all the decimals, and multiplying by 3,500. So we are looking at $4,819.95. So, in looking at what we have now, so I have 4819.95 and checking, and the result is correct.